Hello everyone, the problem that we're going to look at today is problem 7.24 from Fundamentals of Heat and Mass Transfer by Bergman and Levine. The problem is stated as follows. We are told that steel, which is AISI 1010, plates of thickness equal to 6 millimeters and length equal to 1 millimeter on a side, are conveyed from a heat treatment process and are concurrently cooled by atmospheric air at a velocity of U infinity, so the free stream velocity of 10 meters per second, and a free stream temperature of 20 degrees Celsius in parallel flow over the plates. And it says for an initial plate temperature of Ti is equal to 300 C, what is the rate of heat transfer from the plate? What is the corresponding rate of change of the plate temperature? And it also tells us that the velocity of the air is much larger than that of the plate. And essentially what that's trying to say is as these plates are moving on the conveyor, the ratio of movement from the conveyor compared to the air flowing over them is going to be very low. So we can only look at the air essentially flowing in this cross flow and don't have to look at the movement of the plates by the conveyor. So decomposing the problem, what is known about the problem, we know the material properties of AISI 1010, and we're just going to assume those properties at the film temperature. So the difference between our ambient and our temperature of the plates as they're coming out of that heat treatment process. We're also given the dimensions of the plate, so we know that they're 6 millimeters thick and they have a length on each side of 1 meter. We're given our free stream velocity of 10 meters per second, our free stream temperature of 20 degrees Celsius, our initial plate temperature of 300 degrees C, and we can also calculate here our film temperature of 160 degrees C. So the two things we're asked to find, the first one is we want to find the heat transfer rate from the plate, or Q, and we also need to find the rate of the change of the temperature, which is going to be dt over dt. Looking at our schematic here, as we looked at before, we have the plates coming off here with our 1 by 1 meter dimension, and we have this air which is coming in a cross flow. So this is going to be flow or forced convection over a flat plate. And some assumptions that we're going to make, the first one we were told, so we're going to neglect the conveyor velocity as the plates are moving. We're going to assume that the plate as well as the air all have constant properties which are not changing with temperature. We're actually going to use TF, or the film temperature, to calculate all of our properties for the air as well as for the plate. And we're also going to neglect radiation from the plates. So going through our calculation here, the first thing we'll do is calculate our Prandtl number, which is going to be mu Cp, which is our dynamic viscosity times our specific heat, over Kf, which is the thermal conductivity of the fluid. And that's going to give us a Prandtl number of 0.6915. We're also going to calculate our Reynolds number over the length of the plate by taking rho U infinity, which is our free stream, times Lc, which is our characteristic length, over mu, again, the dynamic viscosity. And that's going to give us a Reynolds number of 336,000 approximately. And so what we know is that for external flow over a flat plate, the critical Reynolds number is going to be about 500,000. So we're actually going to assume that our boundary layer is going to be laminar across the entire plate. So since we know it's laminar and we want to take an average heat transfer across the entire plate, we have a film temperature and our Prandtl number is greater than 0.6. The equation we're going to use is this empirical correlation, which is the average Nusselt number over the length is going to be equal to 0.664 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. And so we can plug in our Reynolds number and our Prandtl number as we calculated, and we'll get a Nusselt number of 340.54. We can then use that to find our average heat transfer coefficient across the entire plate by taking the Nusselt number times K, the thermal conductivity, over L, our characteristic length. And that's going to give us an average heat transfer coefficient of 12.1437 watts per meter squared Kelvin. So to calculate our total energy dissipation, or our heat transfer rate, we're going to use this equation. So we're going to use Q. We're actually going to put this 2 out front, and this is essentially just saying that we have both sides of the plate which are being cooled simultaneously. And we'll take our heat transfer coefficient our area of each side of the plate, and then our difference in temperature between our free stream velocity and the initial temperature. And that's going to give us, for each plate, a heat transfer rate of 6,800.48 watts. So then we're asked to calculate the change in temperature over time, or how fast the temperature is decaying over time. And to do that, we're going to use this equation. So we're going to take dt over dt is going to be equal to Q, which is our heat transfer rate that we just calculated, over rho times V. In this case, V is going to be the volume of the plate times Cp. So this is actually going to be the heat stored in our plate. And what we can see when we take those values, we're going to get an approximate cooling rate of 3.334 degrees Celsius per second.